All right, so in this video, we're going to look at a span of vectors, and we're going to determine whether or not a vector is in the span of a set of vectors or not. Now, we're going to look at a two-dimensional example, and basically, as long as these two vectors are independent of each other, then our other vector, our two-dimensional vector, will in fact be in the span. This is not necessarily guaranteed if you have two vectors and they have more than two dimensions, but the math will work out more or less the same way, although you could have a solution that has an inconsistent answer. If these are multiples of each other, then the vector might be in the span or it might not be in the span. But in two dimensions, this is the easiest possible case, and it gives us a chance of just thinking about what the span means. So if 5, 2 is in the span, then that means that there is some linear combination of our two vectors. Oops. 3, -1, such that the result is our 5, 2 vector. Now, we can think of this as a system of equations where essentially we can multiply the coefficients in the vectors by the variables. So a plus 3b is equal to 5, and 2a minus b is equal to 2. So this is our system. Now we can go ahead and solve. We can use matrix methods. So for instance, we can solve our augmented matrix. 1, 3, 5, 2, -1, 2, or we could solve it algebraically using substitution or elimination without matrix form. But in either case, if we go ahead and do row reducing on this matrix, if we take -2 times row 1 and we add it to row 2, and then put it back in row 2, for example, then we would end up with -2 times 1 is -2 plus 2 is going to give me 0. -2 times 3 is going to give me -6. Add that to -1, I'm going to get -7. -2 times 5 is going to give me -10. Add that to this one, and I'm going to get 8, -8. And then I divide everything by -7 in my second equation. And that is going to give me a 1 and 8/7. And then what I can do is I can either back solve or I can do one more step of row reducing in order to get rid of that 3. So let's do -3 row 2 plus row 1 goes back to row 1. And if I do that, -3 times 1 is going to be -3 plus 3 is going to be 0. But then -3 times this is going to be -24/7 added to 5. 5 is going to be 35/7. So 35 minus 24 is going to be 11/7. So what this tells me is that A is 11/7 and B is 8/7. So since the system, I can solve for A and B, that means that, and even if it's dependent, as long as it's consistent, that means that the 5, 2 vector is in fact in the span. And these are the multiples I need of my original vectors in order for that to be the case, to get to the 5, 2 vector. So let's just double check. 11/7 times our vector 1, 2 plus 8/7 times our vector 3, -1. And when we add those up, we're going to get on top 11/7 plus 24/7. And then on the second one, we're going to get 22/7 plus -8 minus 8/7. And so up top, we're going to get 35/7. And on the bottom, we're going to get 14/7. And that's going to reduce 35 divided by 7 is 5. And 14 divided by 7 is 2. So this is our proof that 5, 2 is in the span of our original 2 vectors.